Hello everyone, welcome to the first lecture of the 9th week. In this week, we will explore Taylor's theorem, Maclaurin's theorem, Taylor's series and related some problems. So, the first lecture contains only Taylor's theorem and its mathematical proof. So, let me give you the Taylor's theorem and its statement in a mathematical form. So, a statement says that let a function f from a closed interval a and a plus h to r. So, we have a closed interval a and a plus h, and we are taking a function on the real line r here. This is the function such that if n minus 1, the n minus 1th derivative is continuous on a closed interval a to a plus h, and the same n minus 1th derivative is differentiable on open interval a to a plus h. Then there exists a real number theta satisfying theta lying between 0 to 1 such that f of a plus h is equal to f a h into f dash a plus h square by factorial 2 f double dash a plus of h n minus 1 n minus 1 factorial f n minus 1 and plus some remainder. So, this is the remainder h p power n 1 minus theta n minus p p into n minus 1 factorial f p power n a plus theta h, where p is a positive integer and usually taken as less than or equal to n, right. So, this Taylor's theorem is to find out the approximate value in the neighborhood of a given point. So, here the given point is a and I want in the neighborhood this one. So, here, so I want here h. So, a plus h, this point become a plus h, and I want how my function, I knew the value of f of a. So, I knew how the function behave at a, and I tried to find out the unknown quantity in the neighborhood of that point. That means, I want to execute or I want to find out or approximate this function in the neighborhood of a, and in a precise manner what will be the value of a function at a plus h if f a is given. That was the first type of approximations, and I mean invented by the Taylors, and that's why it's in the honor of them. The name is the Taylor's theorem. So, how to prove this one? Proof is quite easy if we go one step by a step. So, since n minus 1th derivative is continuous on a closed interval a to a plus h, that means all those function f, the first derivative of f, second derivative, third derivative till n minus 1 is continuous on a closed interval. Similarly, all these are differentiable on an open interval a plus h, right. So, now construct a function. So, consider a function psi or phi, phi is a function here. So, consider phi as the same a to a plus h to r closed interval. F phi x is equal to f x plus of a plus h minus x f dash of x and so on, a plus h minus x ka whole square factorial 2f double x and so on, right. And then the last term is capital A plus h minus x power p, where capital A is a constant to be determined. It is unknown constant, A is the unknown constant, and it is determined in such a way where phi a become phi a plus h. So, I am going to take the constant so that the end points value are the same. And I mean you have already done this one in using the Rolle's theorem, mean value theorem and so on, Lagrange mean value theorem and Cauchy mean value theorem. So, phi a plus h equal to phi x gives phi a plus h equal to phi a, not x, right. So, that will give you phi a f a plus h f a plus h f dash a h square factorial 2 and so on. So, let me take this one here, right. So, we have taken this one phi a equal to phi a plus h. So, this will give you a into h by f a power p or E equal to 1 by h power p into f a plus h minus f a minus h f dash a minus so on, right. Since phi is continuous on a closed interval a plus h, since and f the first, second to till n minus 1 derivative are continuous in a closed interval f a plus h. Similarly, it is differentiable and all the derivative of n minus 1 function is differentiable an open interval. Then also phi a equal to phi a plus h here. So, using all these three by Rolle's theorem, there exists a real number theta, and from where to where, theta lying between 0 to 1 such that phi dash of a plus theta h equal to 0, right. So, you have remembered that at least one theta, at least one value of c exists such that f dash of c equal to 0 lying between a to b, right. That was our theorem, Rolle's theorem. So, how to manipulate this one? So, here we had manipulated that if theta lying between 0 to 1, then phi dash of a plus theta h must exist, must hold. And phi dash of x has been constructed in such a way, see, f x plus of a plus h minus x f dash of. So, phi dash of x become f dash of x, and here this will become minus 1 into f double dash of x, and this will become triple dash of x and so on. So, phi dash of x become f dash of x minus f dash of x, a plus h minus x f double dash of x and so on, right, so on. And the last term, that was a into, see here, the last term, that is a into a plus h minus x power p, that will become p into a plus h minus x power p minus 1, right. And manipulate all these functions in a similar way. This will going to be f dash of x minus f dash of x cancel out, a plus h minus x double x plus, and this will minus is cancel out. So, all these terms are going to be cancel out and only two terms will left. The last term, that is, let me erase this, yeah, that is a plus h minus x n minus 1 factorial f power n x minus p a into a plus h minus x p minus 1. These two terms are only remain, which is not going to be cancel out each other. So, that means phi dash of a plus theta h equal to 0 will give you, putting the value of x equal to a plus theta h here. So, a plus h minus of a plus theta h here, see. So, this will comes out to be a cancel out, theta h minus of theta h. So, here take the h common. So, it will gives you h into n minus 1 minus theta by power n minus 1 factorial into f n a plus theta h, that is equal to p a h p minus 1 minus 3 p t minus 1, and you can find out a from that expressions. So, a become h by power n minus p 1 minus theta n minus p divided by p into n minus 1 factorial f n a plus theta h, and therefore, f of a plus h now can be written as, see here, a plus h now can be written as this one, now can be written as, put the value of a there, f a h f dash a h square factorial 2 f double dash of a and so on, and the last term become this one, a into h by power p. So, this value, right, where theta lying between 0 to 1. So, that was the Taylor's theorem, and we have mathematically proved by constructing a phi function such that a, the constant coming in the phi x a can be chosen as phi a equal to phi a plus h. So, the last term h n 1 minus theta n plus n minus p into n minus 1 factorial f n into a plus theta h is called the remainder after the n terms, and it is denoted by R n. and it is called Solomonic rock form of remainder. So, if P is equal to 1, then Rn become h n 1 minus theta n minus 1 n minus 1 factorial f n a plus theta h, right. And in that case Rn is the form of the Cauchy form of the remainder. If P equal to n, then Rn become h p power n factorial n f p power n a plus theta h, and in that case Rn is called Lagrange form of the remainder. So, as you can see, if you at least understand the statement of the Taylor's theorem, then you can put the value of p equal to 1 and p equal to n. So, p equal to 1 will give you the Cauchy form of the remainder and p equal to n will give you the Lagrange form of the remainder. So, these are the remarks for a Taylor's theorem. Taylor's theorem with any particular form of remainder can be proved independently by suitably defining the function phi. Particular form of the remainder can be proved independently. Anytime you can independently prove by suitably defining the function phi. The last term of phi x is equal to a into x plus h minus x by power p is to be chosen as a into a plus h minus x or as a plus h minus x by power n, right, according to as r equal to p equal to 1 or p equal to n, right. P equal to 1 is the Cauchy one and p equal to n is the Lagrange one, right. So, it can be easily proved independently Cauchy form of the remainder and Lagrange form of the remainder. Note 2. Taylor's theorem is the nth mean value theorem. Lagrange mean value theorem is a particular case corresponding to n equal to 1. So, the Taylor's theorem is the generalized version of the Lagrange mean value theorem, where Lagrange value theorem is nothing but n equal to 1, and this Taylor theorem is the nth mean value theorem, right. And the third one, the theorem also holds if h is less than 0. Obviously, I mean, we had not put it too much pressure on the h is just taking as a constant. You can find out. So, we had a and a plus h, we can have this one as a and a minus h. Nothing has been changed, everything will be in the same line. In this case interval, a into a plus h is to be replaced by a plus a minus h to a, right. So, this is a minus h to a. We have done this one, right. Here a to a plus h, and if it is remainder, then here a to a minus h. This is the thing, right. So, Taylor's theorem in another form, that is called, we call it the second form. Let a function f defined in interval, closed interval a to a plus h as a real valued function, such that the n minus 1th derivative is continuous in the closed interval and differentiable in the open interval a to a plus h. Then for any x belongs to the open interval a to a plus h, there exists a real number theta, where theta lying between 0 to 1, such that f(x) can be written as f a plus x minus f dash of a plus of x minus a ka square factorial to f double dash of a, and so on. And this is the last term, where p is a positive integer taken less than or equal to n, right. So, now in the first one you have seen that we have taken a to a plus h as a real valued function, the whole real number r, and we try to find out the value at this point, right. So, f a is given and we have tried to find out the value which are approximate value of the function in the neighborhood of that point a, right. Here it says that if x lying between not an end points, but at any interior point of a to a plus h, f(x) can be approximated in terms of f a, and that is a very beautiful thing, right. So, f a is given and you have to find out f(x). So, I mean the proof is on the similar line and one can prove very easily. Since f satisfies the conditions of Taylor's theorem on closed interval a to a plus h, and since x belongs to a to a plus h, f satisfies the condition on a to x, right, on the closed interval a to x. You had already countered that a to a plus h, x lying between somewhere here. So, let us say x is lying between here. So, that means in the whole interval Taylor's theorem lying, Taylor's theorem satisfied. So, Taylor's theorem also satisfied this interval, this closed interval a to a plus h, a to x. So, in the interval a to x closed interval, f satisfied the whole condition, that means it is n minus 1th derivative is continuous and that interval closed interval a to x differentiable, n minus 1th derivative of the function is differentiable in open interval a to x and so on. So, I can write this one as x replacing x as equal to a plus h and then the Taylor's theorem valid. So, the second form of the Taylor's theorem will be proved easily by using the first form of the Taylor's theorem by putting x is equal to a plus h. So, in place of x you just a plus h and then it will be the answer. So, for an independent proof of the theorem in this form, consider the function phi a plus x as a real valued function and then construct phi t equal to f t x minus t f dash t plus x minus t ka square factorial 2 and so on, and in the last term we have a into x minus t ka whole power p for t belongs to any number a to x, right. And if you are putting this one value, then a bill comes out to be the similar manner 1 by x minus of t power p and so on, and then put the value of this, then the proof is directly coming out. Now, very closely related to Taylor's theorem is Maclaurin's theorem. And what is the Maclaurin's theorem? If you put the one of the endpoints a as 0 and taking the increment only as h. So, in a closed interval 0 to h, a function is defined as a real valued such that n minus 1th derivative of that function is continuous on the closed interval 0 to h and differentiable on open interval 0 to h. Then for x belongs to 0 to h, there exists a real number theta satisfying theta lying between 0 to 1 such that f of x can be written as f0 plus of x f dash 0 x square by factorial 2 f double dash 0 and so on, and the last term will be x power n 1 minus theta n minus p divided by p n minus 1 factorial f power n theta x, and where p is nothing but a positive integer taken less than or equal to n. Here, how to prove this one? So, if I put a and a plus h as a closed interval, then we had seen that for a Taylor's theorem, f of n minus 1 is continuous in closed interval a to a plus h and differentiable in an open interval a to a plus h, and if it happen then there exists a theta lying between where to where 0 to 1 open interval such that this happen a plus h is equal to something or f of x equal to something, right. Now, put a equal to 0 and everywhere you will find out the answer. The second form of the Taylor's theorem, the second form of the Taylor's theorem gives Maclaurin's theorem if a equal to 0. Just look at the structure and you will find out that is it true or not. So, see here f of x equal to f a plus of x minus a factorial a. So, put a equal to 0 everywhere. So, what it will give? F x equal to f of 0 plus of x into f dash of a and so on. So, see here f of x equal to f0 x into f dash of 0 x square by factorial to f double dash of 0 and so on. So, that is Maclaurin's theorem, and these two statements are quite important to find out. So, how to prove this one, and there are some remarks over this theorem. So, taking a equal to 0 in a Taylor's theorem of the second form, obviously I have to write down Taylor's theorem of the second form. It reduces to f x 0 equal to f 0 plus x into f dash 0 and so on, and the last term become x by power n 1 minus theta n minus p divided by p into n minus 1 ka factorial f by power n theta x. The last term is called the remainder. This remainder after n terms, and it is denoted by Rm, and it is also called Solomik-Roque form of the remainder theorem, the remainder. And if I put p equal to 1, it will give you a Cauchy remainder theorem, and if I put p equal to n, it will give you the Lagrange remainder theorem. The Cauchy form of that remainder Rn can be easily written here. See here, n equal to 1, put the p equal to 1. So, this will comes out to be xn into 1 minus theta, and that by power n minus 1 divided by n minus 1 ka factorial, right, and this will comes out to fn theta into x, right, this one. So, this a equal to 0, here. So, fn theta x. Similarly, if I put p equal to n, so if I put p equal to n, xn divided by factorial n, and n minus p becomes 0. So, 1 minus theta wholes become 1, and n minus 1 factorial into p equal to n. So, n into n minus 1 factorial become n factorial, and this will comes out to be fn and theta of x. So, it is not a, because this is going to be 0. So, that is the Lagrange form for the Lagrange remainder of the Maclaurin's theorem, the Cauchy remainder of the Maclaurin's theorem, and Maclaurin's theorem itself for the n term remainder, right. So, I believe that this will enhance your concepts in Cauchy theorem, Cauchy form of the Taylor's theorem, Lagrange form of the Taylor's theorem, Maclaurin's theorem, and nth remainder of the Maclaurin's theorem, the Cauchy form of the remainder for the Maclaurin's theorem, as well as the Lagrange form of the remainder for the Maclaurin's theorem. And as you look at this one, we had only explored the continuous and differentiable function such that n minus 1th derivative of the function is continuous in the closed interval a to a plus h, and differentiable in an open interval a to a plus h. That will lead to the Maclaurin's theorem. But once you have the second form of the Maclaurin's theorem, you can easily find out once you have the second form of the Taylor's theorem, you can easily find out the Maclaurin's theorem by putting a equal to 0. So, that will makes you the function is continuous, n minus 1th derivative of the function is continuous in a closed interval 0 to h and an open interval in 0 to h, and the whole function will become the Maclaurin's theorem when putting a equal to 0. So, that is the idea. You have to just go through the first theorem, that is the Taylor's theorem of the first form and the second form. You will find out easily by putting a equal to 0 as the Maclaurin's theorem. One more important thing, and as a remark, you have to remember that when you will take h less than 0, the interval you are talking about a to a plus h is now become a minus h or a plus h to a, right. So, that is the easy thing, that is the noteworthy thing. So, thank you so much.